Welcome back, everybody. So for this second talk of the day, we have Benjamin with a third lecture on non-equilibrium quantum mechanics.
Okay, yes. So today, my plan was to start in the third lecture start talking about fluctuations, but I now want just to finish the first bit of the lecture with the hydrodynamic description of these non-equilibrium steady states. So I gave you last time, I explained how one can get to the free fermion and understand the Liouville equation of conservation of phase space in terms of an earlier hydrodynamic equation in free fermions. And one can go further. Free fermion is okay, but it's a bit easy. One can go further and then do actually every integrable system, the hydrodynamics of every integrable system, and get a solution for the non-equilibrium steady state, which generalizes the CFT solution in some kind of natural fashion to all these integrable systems. And I just want to express the result in the physics and not derive the result because it's a bit too much. But just a few recall, so we want to do the local thermalization, maximum entropy states and all that, and then calculate equations of states, so average densities and average currents, and write continuity equations. That's what we do, okay? So just the main formulas we have a free energy in the free fermionic system. Now I'm going to write it in terms of some kind of integration over rapidity, say in a relativistic system, okay? And it takes the usual form of the free energy for free fermions, say, which is something like that, where this epsilon is just the thing that is involved in the state determined. So the state is, I think I had written that. So is rho is exponential minus integration d theta on w of theta and a dagger theta a theta, right? Something like that. So something where you excite every quasi-particle with a weight w of theta. Okay. So this is the free energy, and the average densities always have the form of derivatives of the free energy with respect to the beta i's. The beta i's, well, the w of theta is just linear combination, sum over I of the beta I times some function, which is the one particular eigenvalue of the conserved quantity I. For instance, that could be, for instance, H1, H0 for the energy, that would be cosine hyperbolic theta, H1 for the momentum, that would be sine hyperbolic theta. But then you have, infinitely many more in your quantum field theory that is integrable. Or you have whatever, how many you have, right? But in integrable quantum field theory, you're going to have infinite. In fact, you can have any function of theta there, and the NW of theta is an arbitrary function of theta. So we had said that in free fermion models, and that's is the case here. And so this then takes the form of integration d theta p prime of theta, if you do the calculation, times this one particle eigenvalue, so the quantity carried by this conserved charge, and times some distribution n of theta, which was nothing else but 1 over, right down here, 1 over 1, the Fermi distribution, e to the minus epsilon of theta. I call this epsilon, but here is just w, right? It's the same thing. Epsilon is w. And so that determines the conserved densities. And we have also something for the currents. So if we remember the currents, well, they took the form, well, here I write it kind of marginally in the integrable model, in the relativistic model is integration with E prime of theta is essentially the group velocity. Here, the derivative with respect to theta. Now there's hi of theta again, and there's this n of theta again, okay? So this is what the currents look like. And then you just have to write down your equation of continuity is equivalent to or implies the continuity for this n. I had called it rho, but I'm going to call it n now. And if I want to be precise, I think it's a factor of 2 pi's, but they don't matter too much. Okay. So now we have dt of n plus, if I put things together, I have the velocity v of theta and, well, v of theta, and depends on theta, xt, okay, etc. And it's equal to 0, where v is the group velocity. So v of theta is e prime of theta over p prime of theta, or dE dp. Right? So here I'm writing everything in terms of rapidity to do the relativistic case, relativistic KFT. Okay? So this is the situation that we have in free fermion models, relativistic free fermion. Okay? Now there's one thing, you see that there's some space missing here. In fact, the currents, you can also write them as a derivative of some kind of free energy with respect to beta. Function G, this is some kind of free energy flux. And it turns out by completely general arguments of statistical mechanics, there always exists a function of the betas whose derivatives give the currents. So the free energy flux always exists. This is a consequence of statistical mechanics. So not only there's a free energy that gives the densities, there's a free energy flux that gives the current. In CFT, it's easy to calculate. One is equal to the other. But in general, this always exists. And you can write it explicitly in the form similar to a free energy, except that instead of the P prime, instead of the measure being dP, the momentum, the measure is dE, the energy. And you have log of 1 plus e to the minus epsilon of theta. Okay. So this is the structure that you have in free fermion models, the thermodynamics of free fermions, right? It's just basic stuff, right? Basic thermodynamics of free fermions, but including also the currents, not just the densities, but also the currents. Okay. Now it turns out that you have something very similar for every integrable system. You can write very similar equations. I'm just going to modify the equations for integrable systems by using another color. This, the free energy and the free energy fluxes, they take exactly the same form for interacting integrable system, okay? Except now this epsilon that's involved there is not directly the W that's there that weighs every quasi-particle. So in integrable system, you still have quasi-particles because you have factorized scattering. So okay, so you have quasi-particles, you can weigh them with different weights. And that epsilon that arrives there is modified. There's an additional term, and the term is non-trivial. And it involves what is called the differential scattering phase, phi, this is my letter phi of theta minus alpha, times the log of 1 plus exponential minus epsilon of alpha. So this is actually a nonlinear integral equation for epsilon that you now have to solve in integrable system. And that's the consequence of the Bethe-ansatz. So if you do Bethe-ansatz for integrable system, that's what you find. The theta, the theta essentially they parameterize the Bethe roots if you do Bethe-ansatz. So this is something that comes out from your Bethe-ansatz solution. Okay, so this is one difference, and the other difference is that the P prime in all that these become dressed. There's a small dr that you put there. The P prime and the E prime they become dressed. A small dr. Okay, and what is the dressing? Well, it's some kind of a general. It's a integral transform. So any function dress of theta satisfies the linear integral equation. F dress of theta is f theta plus integration. And again, it involves the differential scattering phase. I'll come to what it is just now. Phi theta minus alpha, n of alpha times f dress of alpha. Okay. So this is just a consequence of doing the derivative of that free energy using that non-trivial integral equation, and you get this other integral equation. Okay? So you've got to solve some integral equation, put them there, and then you write your conservation law, and you get exactly the same thing, dtn plus vdxn, but except again the velocity has a dress in it. In fact, this is the effective velocity. Actually, by just effective velocity in our cases, it is the eigenvalues of the flux Jacobian. Okay, so this is the structure. There's a small modifications that you do to the free fermion case in order to get the interacting case, and the additional data that you put in it is this phi. So in integral models, you have a factorized scattering. You can imagine two particles kind of coming together, scattering there and coming out. And because it is factorized scattering, the momenta always are the same. And the scattering matrix for two-body scattering, which is in relativistic model depends on the difference of rapidity, is some phase e to the I phi of theta minus alpha. And the differential scattering phase is just the derivative of that phase phi. So that's the data you need from your integral model. If you know how two particles scatter with each other, if you know the scattering, well, you put that in here and you get the hydrodynamic equation for an integral model. So this is just kind of expressing the formula. How you derive that is by using Bethe ansatz. So the thermodynamics derived by using Bethe ansatz, and the current is derived by using various. Well, we first derived that by using crossing symmetry, actually, over specific quantum field theory. Crossing symmetry was the trick we used to calculate the currents. But then there are other ways of calculating the currents by form factors and all that. Okay, so this is the formula. Yes.
Can you just comment on the name dressed? Like, why is it called like that?
Yeah. So this is what it's called. Yeah. So you see, there's an F dress there. F dress. So this is a linear integral equation. It actually kind of represents the actual momentum. Well, like this velocity. Right? Yeah. So let me discuss the velocity for you, which is kind of a ratio of dress stuff. That has the most physical meaning, actually. Okay. So this velocity that appears there is the dressed velocity or effective velocity that the particle sees while it goes within a gas of many other particles and interact by scattering like that with all these other particles. So if you look at the particle, so it goes like that, right? At some velocity. The velocity is tangent hyperbolic theta, right, in relativistic model, right? But if there are many other particles, well, it's going to interact with these other particles. So what does it change if there are many other particles? Well, it's going to start straight and then maybe hit the particles. There's an interaction, a differential scattering phase. And by semi-classical argument, what if you imagine a wave packet and some interaction with the scattering phase, what does the wave packet do? Well, it will shift a little bit. So this d theta phi is a spatial shift of semi-classical wave packet. And if you do the semi-classical analysis of two-body scattering. Because as if it's shifted a little bit kind of actually backward like that by this phi of theta minus alpha. This is theta, and now you have it hits another particle like that, which is alpha. And so now there's a bit of a shift. I continue with the white like that. And now it starts there and continues. Then it hits another particle, so it shifts again like that, like that a little bit. Then it hits another particle, perhaps that goes like this and shifts. So there's a lot of shifts that happens because of the scattering, and the overall trajectory looks like more something like that. Kind of overall trajectory is this. There's a difference of slope, and that slope is the effective velocity. So the dressing takes into account the multiple interaction of the particle within the gas of particle. That's just kind of a semi-classical physical picture. This is a result of calculation. That's the a posteriori interpretation. And yeah, and then so the currents takes into account the interaction with all the particles, and then you have a hydrodynamic equation that you can use to solve the problem of kind of the steady state problem. Okay. Now, yeah, okay. Questions about this? It's a bit, you see, there's a kind of dual picture here. The quasi-particles are the actual quasi-particles that are there in your model. These are the asymptotic particles of your theory. It's quantum field theory. It has a set of asymptotic particles. So these are that, right? But at the same time, this is also hydrodynamic theory. I do thermodynamics. I do the local maximization of entropy here, because I take averages of densities and currents in some local state described by this thermodynamics. Okay? And now these theta, the i's that are there, instead I've used the thetas, right? I go from the i's. So these theta are also the hydrodynamic modes. So the asymptotic particles of the integrable theory become the normal modes of the hydrodynamics in integral models, it's particular integral models. And how are they modified from asymptotic particle to actual modes? Is that velocity is a bit different, right? That knows about the gas within which the particle is. So this is no longer really a well-defined asymptotic particle. There's some kind of effective degree of freedom, which is really a hydrodynamic degree of freedom. And that one goes at certain velocity. So this is the ballistic mode propagating. That's the ballistic transport of hydrodynamics, which is a bit of a kind of a modified version of just free, transport of a free asymptotic particles of the QFT. But there is this mapping from asymptotic particles to the hydrodynamic mode. In fact, the mapping can be quite non-trivial. This is the simple situation. If you have non-diagonal scattering, then the asymptotic particles are no longer the hydromodes. You need to diagonalize the scattering, the TBA, and all that, and you have new hydromodes that come out. Then there's the basis strings, there's all kind of things coming out. Okay, it can be more complicated, but there's some kind of mapping. Okay, so this is all kind of a little bit technical, and yeah, why is that all these equations are true and all that? It's quite a lot of calculation, but just to say, there is a hydrodynamic theory for integrable system. Sine-Gordon model, for instance, will do the job. XXZ chain as well, or Liebniger model. So they all have this equation. Once you have that, then you can solve the steady state problem. So the stationary state. So, and the solution is, you just solve the earlier equation that I wrote last time. I just write the solution. So the stationary state in array eta at a rapidity theta is nothing else. It's very simple, because I told you these normal mode, they just follow the characteristics, right? So you just have to go back in time and see where it comes from. So this stationary state solves a certain equation, which is that it is equal to n left. So the occupation function, interacting occupation function for the left reservoir, theta eta, if the effective velocity of that mode at that ray is greater than the ray. Otherwise, it is n right. So if the effective velocity of that mode in that ray is smaller than the ray. And the picture is extremely simple. Picture is, you have this, you look at a certain ray, you look at the point there. If the velocity is in that direction, then the particle must have come from the left. While if the velocity is in the other direction, so smaller than the ray, then the particle must have come from the right. And you just thermalize the particle, that not quite a particle, but that hydro mode, according to where it comes from, because the normal mode just carries the state on the characteristic line, right? So this is actually this, if you think about that, it's a non-trivial integral equation, because the effective velocity involved the dressing involved the state itself, and because it's all the particles hitting each other. And so you have to know n in order to determine if this is greater or not. But n, is determined by, it's the sum of these two things. So you have to solve that by recursion. There's you have to do numerics to solve that. So this is the effective velocity in the stationary state. But it's actually not very complicated to solve. I mean, it's easy to solve numerically, and then you get explicit curves for what the state looks like on every ray. It's a nice smooth change of state between the two lines, between the plus or minus velocity plus or minus 1. And you can compare that with numerics if you do quantum spin chains, for instance, and it all works. So that's it. Yeah. Okay, so that's what I wanted to say about the non-equilibrium steady state. Starting with the CFT, which was nice and simple and clear, although it with the integral models, which is much more complicated, but still correct. Well, and a generalization of the CFT, which to more complicated modes, hydromodes, which are these quasi-particles instead of the left and right mover. Okay. So now that was part 1, the non-equilibrium steady state. Okay. Now I want to go to part 2, which is about fluctuations. So I'm going to go back to something simple. So forget about integrable systems. If you didn't understand that, doesn't matter. We're not going to use that at all. So what we did conformal field theory at the beginning. So now let us think back about this conformal field theory and the right and left mover. It's sufficient to understand the main thing, and then slowly make it more complicated. Okay. So the first thing now, so I want to kind of pose the problem a little bit. So what is it that we want to do? So I was thinking about T left and T right as an initial state, and letting the state evolve, and then seeing what happens. Something happened here, there's some stationary state there, maybe there's some Lycon effect and some slow change or something like that, but there's a state here at very large time at x equals 0. Okay, so that's a state that carries momentum. So in conformal field theory, the average momentum was just C pi over 12 t left square minus t right square, right? So fine, so there's a current. So I can start with something that's time reversal invariant, and in the end, I get something that is not time reversal invariant. Now, we would like to know a little bit more about that state. In fact, we can even ask more about I kind of state, but in particular about that non-equilibrium stationary state, okay? And what, if you do thermodynamics, for instance, the averages, the average energy, the average pressure, now that gives you something, but there's more within thermodynamics, right, than just averages, okay? What more is there? Well, there are the fluctuations. So you know that in thermodynamics, fluctuation of total energy, for instance, well, they're very small, right? The energy is almost surely total energy is that, but there are some fluctuations. Law of large number is a Gaussian fluctuation, right? In fact, you can go a bit further and see kind of the rare fluctuations. Maybe the total energy is almost surely that. It fluctuates a little bit. Sometimes it does something weird, kind of not so often. And you can measure, what happens when it does something weird. And in fact, these are kind of universal quantities and things that tell you a lot about the state. Okay? Now, out of equilibrium, so what I mean here, what can I look at out of equilibrium? Well, the momentum, the energy current, is how much energy has passed, say, from the left to the right over a certain time, right? So that's the current. If you integrate the current over time, you get the total amount of energy that has passed from left to right on that time, okay? So let me think now about, this is my stationary state. Just look at the stationary state. So this thing is that. Stationary state, I've constructed its non-trivial state. I kind of know how to write it now that, okay? And I want to know that indeed. I want to, okay, so this is I have a interface there, okay? And I'm looking at the quantity of energy that has passed from left to right. I mean, sometimes energy will go from right to left, but most of the time from left to right if T left is greater than T right. I guess I have a current towards the right. Okay. So this is a quantity that I can write. So what's this quantity? It's say total current J of T. So integration, say, from minus T over 2 to T over 2 of the current at position 0 and time S ds, okay, total current. Okay. The number of quantity of energy passing from left to right. Okay. And so this is at large T. So supposedly it's maybe like in thermodynamics, so at large T that's going to go to something almost fixed. What's going to go to at large T is going to go like T times, where I use J instead of, I'm going to use J if you don't mind. So the current T times the average current J, right, in the stationary state at large T. But this is not an average. This is an operator, right? Or you can think of that even as a fluctuating thing, a random variable, right? So it's not equal to that. So it fluctuates. And how does it fluctuate? What are the fluctuations? So that's what I want to get to. What the fluctuations are of this quantity. Okay, so its total current goes something, but there are fluctuations. Maybe I can ask the question for any t, any time, and see what the fluctuations are. But it turns out that there is a nice structure that one can get to if the time is large. You can understand the fluctuation for large time and see what these are. Okay. So this has to do with the something called large-deviation theory. But for now, so what I can think of, are we? Yes. So you see, this is a subtle question. It depends what you mean. So, indeed. So, it depends how you scale things. Actually, when people say, you have a law of large number, this large T is Gaussian. So, we could expect this to be Gaussian, right? You look at the current over a very large time, it fluctuates a bit like that, but there's a lot of cancellation of these fluctuations, and basically is that average plus something Gaussian, right? But when we say that, actually what we mean is that is the average, which is very large, plus something Gaussian, which is very small, right? And then it's Gaussian, and then you say everything else. But in fact, if you look at even smaller, and if you are ready to scale the cumulants up enough, then the other cumulants will also be non-zero. So anticipating what is the situation? So this is J of T. Okay, I would like to calculate its average within the stationary state. Right? And maybe its cumulants, it's better to calculate the cumulants, right? Subtract the statistically is better. Okay? And I want to know how it goes. And the situation, so kind of what is actually happening, or what one expects often, and okay, what is, we can calculate what's happening, is that the cumulants, in fact, all the cumulants there's an n, say, for all n, cumulants for all n powers, they will all scale like t times something, some number Cn, plus something smaller in time. Right? So is it Gaussian? Is it not? Well, if you are to rescale j and goes, rescale it by square root of t, j goes to j over square root of t, you would get something non-zero for infinite for C2 and 0 for all other Cn, for all other n, because you would have a square root of t to the power n in the denominator. Okay? And that's a usual statement of Gaussianity. You take your current and you rescale by 1 over square root of t. You subtract the average and rescale by 1 square root of t. And then you see that you have a non-zero second cumulant and 0 higher cumulant. Okay? But if you rescale your current differently for higher n, then you find something non-zero. And the statement is that, well, for all cumulants, it's proportional to t, something proportional to t that you find. So it is Gaussian from that point of view of the standard rescaling, but there's more to it than Gaussian, and is that. Why? Where does that come from? Well, it's a little bit, so if you repackage that into, so you can think about taking the average of the exponential lambda j of t, okay, in the stationary state, that's just repackaging the cumulants, right? So this is the sum n from 1 to infinity of lambda to the n over n factorial, the nth cumulant, okay, in the stationary state. So maybe I don't write star now everywhere. So this is just a way of defining the cumulants by average exponential. Okay, and so you see then that this goes like, so sorry, I'm missing a log here. Of course, I'm missing a log of that. Yeah. So now this will go like t times the sum n from 1 to infinity lambda to n over n factorial times the number Cn. And this is what we call f of lambda. They're going down a bit by themselves. This is the scaled cumulant generating function, SCGF. In the condensed matter literature is something called the full counting statistics as well. Here, the problem is calculating the scale cumulant generating function, or even more or better, first showing that the log of that average indeed grows like t. So all the cumulants grow like t, and finding the coefficient with f of lambda. Yeah. Oh, yeah. So this is smaller than t, small o of t. Yeah.
What's the order of the introduction?
Yes. I do not know. I do not know. Yeah. You might. I'm not sure. You might even expect some kind of square root of t for diffusive behavior or something like that. I think, but it's not so well understood right now. It depends on the problem in nowadays. Yes, that would expect square root of t if you have a diffusive behavior. Yeah, something like that. Yes.
Another question is, do you include even a log?
Yeah. So that's a good question. I mean, if you are, you see, I can do that at equilibrium, and then all the odds are 0. But now, if I'm in my stationary state, then the odds and even both are non-zero, and both of them sees or shows, at least in some models. That's the difference from equilibrium. But of course, you can ask the question also at equilibrium. But here it's interesting that you have both of them. And out of equilibrium, there's also more things that are interesting, in particular something called the fluctuation relation, which I'll explain on Friday. I'll do the fluctuation relation. So there's a relation between this f of lambda that it depends on the temperatures of the stationary state and depends on it in a particular way, and it satisfies a very original set of relations that are expected, and that are characteristic of that stationary state being something coming from reservoir and all that. So within f of lambda, you can see if that is a non-equilibrium steady state from this fluctuation relation. That's one of the things. Why? One of the interests of calculating is f of lambda. If you have an arbitrary series with Cn like that, arbitrary thing is maybe it's not quite a non-equilibrium steady state, but if it's a steady state with left and right reservoir, then this must satisfy a certain relation. And right reservoir, how do you define that? Well, okay, so like in that situation is the case. So this is an interesting object that encodes a lot of the information about the stationary state, more than just the average, right? And how the fluctuations are in this. Okay? So that's the object to calculate. Now, a bit more of this theory there. So this is a calculated generating function. If you think in terms of the probability, so the probability that j of t, let's say j of t divided by t takes the value j. Let me call that pt of j. Okay. Now, one can wonder what does this probability function looks like at large time. Okay. So what we would like to say is that this should be very narrow, because at a very large time, this j of t over t, that's extensive observable divided by t, that should go just to a fixed value, the average, which is C1, right? Should be narrow around C1, actually, right? Now, that t scaling corresponds to a certain form of that probability distribution, right? So the fact that you have a t in here, t times that, corresponds to a form, and the form that it corresponds to is usually written with this symbol like that, in the sense that this is true in the sense of exponential behavior. So the logs on both sides are agree at large t. So this is exponential of minus t times a certain function of j, that j there, that small j there. Okay. So this function is called the large deviation function. Okay. It's a function that characterizes probability distribution. It has a minimum. So at C1 is just the average current. So that was the thing that I've written there is kind of what I call now C1, the first cumulant is the average current. Has a minimum, which is 0, which is equal to 0, because this is at that point where the probability is maximal, and the maximum that it can have is just 1, of course. So I is 0. Okay, so 0 there, well, like very near to 0. Well, I is 0. The probability is very near to 1 there. And so I of j otherwise is just positive. Okay, so greater or equal to 0, and is 0 at C1. So that's what we would expect somehow to have. Okay, and the question is calculating f of lambda or calculating I of j. These are equivalent questions. And to see the equivalence, you say, well, okay, if I calculate the average of exponential lambda j of t, I think now very classically, right? It's quantum system, but I think very classically. It's like, think of that as a classical variable, right? Where I would do integration of this probability densities pt of j e to the lambda j, right? And then I would put that exponential form, which is exponential minus t I of j plus lambda j, yes, okay, yes, plus lambda j, and there's a t in front here because this is the total j and this is the small j, okay, lambda tj. So what I have, I rewrite this integral dj exponential minus t, there's I of j minus lambda j. Okay. How do I calculate that integral over j? See, there's a j there, there's I of j, there's a t, and t is large. So what I can do is a saddle point analysis. For t large, it's just saddle point. Okay. If I do saddle point, what I will find is that this will go like exponential minus t times a function of lambda, and f of lambda, because I do saddle point, is nothing else but the Legendre transform of I of j. If you do the saddle point, you find equation which are exactly the Legendre transform equation. Okay. So this I of j that characterizes the probability, saying it's exponential, is just the Legendre transform of this f of lambda. And the fact that the cumulants grow like t is related to the fact that the probability is exponential minus t. There's a large, that equation there, this is called a large deviation principle. similarly, this being T times F is large division principle, okay, with exponent 1, because in general, you could have square root of T or T to the 2 or something. You can have other exponents there, but here, exponent 1. Okay, so that's kind of the general theory. There's a current that fluctuates, there's a probability that condensates around something, and then there are cumulants that you can evaluate, and there's a relation about how the probability condensates around something becomes peak around something, and the fact that the cumulants scale likely in a certain fashion. And so the large T behavior tells you about how this kind of subtle stuff about how the variable fluctuates. Okay. Yes.
Just very generic question, because I'm not at all an expert in this. So the fact that the full quantum statistics and the large deviation function are related to the Legendre, is it a general thing in this?
Yeah,
theory,
it's completely general. Yeah, exactly. So if you have a large deviation principle for an extensive observable, then this is what's happening.
Okay.
That's the general thing. Now, there are some very well-known examples of that stuff, and one well-known theory that you know very, very well, which falls within this description, is thermodynamics. Thermodynamics, yeah, so if I do thermodynamics, just to kind of recall just the kind of basic stuff, right? We have a partition function, okay? So it's kind of falls with, it's a bit different but very similar. So we have a partition function, and the partition function, it goes like at large volume, exponential minus my volume is L, okay, times the free energy that depends on the temperature, right? And if you do the Legendre transform of F, what do you get actually for the Legendre transform in thermodynamics? You remember thermodynamics book? Legendre transform of free energy. I wouldn't remember if I didn't know that, but maybe someone. You get exactly the entropy, S, as a function of the energy. So F as function of beta or inverse temperature becomes S entropy as function of the energy. And the entropy is nothing else but telling you the probability of having a certain configuration for energy E. It's something like exponential minus the volume times the entropy, S of E in thermodynamics. You have your fluctuating thermodynamic system. What's the probability of finding the thing with energy E? Well, it's the entropy of that. And of course, you minimize the entropy to find just the right energy of the system. So you might minimize the entropy, which is the same thing as minimizing that large deviation function, finding the average of this, current and all that. So here you would find the average of the energy. So this is a situation where you have free energy entropy. Free energy entropy is the same thing as scale cumulant generating function in large deviation function. Okay. Free energy entropy sounds better, but okay, it's similar. Okay. So thermodynamics is a large deviation theory, essentially, for fluctuations of charges on the volume, and the large deviation parameter, say, is the volume, not the time, but the volume. And now we say, well, we are out of equilibrium, and we try to do the same thing, but in time, for transport of quantities. And so how do you do thermodynamics in time? Well, it's via this large deviation theory thing. So this is the equivalent of thermodynamics, but for transport, for dynamical quantities. So out of equilibrium, then it has a meaning and all that. So that's the general blah blah, let's say, about why you do that, and yeah, what is this? Okay. Yes, questions?
Does this explain why you can express entanglement entropy in terms of cumulants? Is it related?
Yes, it is related indeed. And for that, you see, very much so, right? So entanglement entropy is like an entropy and all that, and you want to express it into a certain cumulus, so it's very much so. Except entanglement entropy is you need to find the right charge that corresponds to it. It becomes an entropy naturally at large volume. If you have temperature, then it's clear. But in other situations, then it's not quite an entropy like that. Yeah. It's a bit different. But yes, yes. No, exactly. There for free system, yeah, for free Fermion it's clear because you can. But in general, it's free. In free boson there is a yes, I don't know in general dimension. I think there would be in free theories there should be, although it's a bit is a bit tricky actually. With in free fermion, but we can discuss that. Maybe we'll discuss after. Yeah, no, but there is, but this no. Well, okay. In general bosonic state, in free theories, there is, because you can diagonalize the twist action, at least for any entropies. For any entropies, maybe not for, you can diagonalize the twist action and write that in terms of general, in terms of non-twist fields. Twist field code. Yes, I think so. Well, we can discuss it. Yeah. No, sure. It's in 2 dimensions is a non-trivial operator, but you can still write it up, write it down. Let's say. Which have to think about it in general. Yes, I don't know. But let's discuss that then. Let's clarify this a little bit. Yeah. Sorry, but I wanted to get to the relation with twist field maybe in the last lecture. Okay. What time is it? I have no idea about the time. Still 20 minutes. Yeah, okay, it's good. So, but before that, I'd like to do some explicit example about that. You know, it's all very general now, isn't it? And CFT is the best toy model, 1+1 DCFT, for doing the example and calculating everything. And everything is kind of nice and clear. Okay. So, how does that work? Actually, maybe I can do even before that a small little example, which is not too bad, and which is not out of equilibrium, but kind of, you know, thermodynamics, okay? Which is general and a bit of a hand-wavy argument, but not too bad. Okay? So suppose I want to calculate now the average of something extensive, but now I'm going to do the average of exponential lambda, the integral, say from 0 to L of some conserved density Qi of x dx in some state. Let me make it even simpler, just not to have too many Qi's now. That I'm going to put the energy density there, H, and this is some thermal state with inverse temperature beta. Okay. So how does that behave? Right, this is a natural question, right? So you have a state, and you put exponential of the energy just on some interval 0 to L. So you want to know how this total energy in that interval fluctuates. Okay. So I can calculate. So this is trace, and then I have exponential of minus beta h, the total Hamiltonian, and then exponentials of lambda integration from 0 to L of the energy density dx. And of course, I must divide by trace exponential minus beta h. So this is the expression. Okay. Now I'm going to do a bit of hand-wavy arguments, and since I'm looking at what happens at large L, maybe I'm hoping that I can mix together this total H and this partial H as if they were commuting with each other. I mean, they don't commute as operator. But if I forget about that, I would say that's kind of not too far from trace exponential, and then I put minus beta integration dx everywhere, h of x, plus lambda integration just from 0 to L, h of x dx, divided by, you know, trace is minus beta h. It's an approximation, and hopefully the large L behavior is actually not affected by the commutators, non-zero commutators. That non-zero commutators will occur on the boundaries at 0 and L, essentially, because in the bulk it's still commute, something like that. So these should not scale with L. Okay, now I put things together a little bit, so I'm going to go this direction. So this is saying what this is equal to now at this moment, equal to, I can write trace of exponential. Now I can integrate minus beta everywhere except between 0 and L. So just the bit of the Hamiltonian outside of the interval. And then minus beta minus lambda everywhere inside 0L, right? Modified, okay? And then I normalize the whole thing. And again, I can write it kind of in the same way, right? Everywhere outside, which has a dx h of x, and everywhere inside, which has, again, dx h of x, but times beta. Okay, so I just divide these terms. There's a outside, there's beta, and there's beta minus lambda inside on the numerator. In the denominator is beta and beta inside and outside. Now I'm thinking, okay, what happens at large L? And this is not a proof, but the result is still correct. What happens at large L? Well, you see that you have you can do good approximation up to terms that do not affect the exponential, separate the trace there's a kind of a factorization, right? So it's a trace of this plus that, it becomes a trace of this times that. You can separate the trace. So that goes like the trace of exponential minus beta, this integration dx outside of 0L, h of x, times the trace of the other one, beta minus lambda integration between 0L. Both are divided by their own numerator, which is just, well, here is the same thing as that. So let me write it. So divided by the same thing, while here is divided by, again, that. So trace exponential minus beta. So I'm just separating the trace. Yeah, is there really factorization? Well, physically, what happens here and what happens very far, well, they're not really related. If correlation decay fast enough, that should be fine. So separation should be fine. If your Hilbert space is the tensor product of Hilbert space in different positions, it factorizes, and these operators are almost factorized. They are non-zero commutators, but they should not affect the large L behavior. Oh, okay. So this cancels out, and now I can use thermodynamics. This is partition function, so exponential minus L free energy at beta minus lambda, and the other is plus L free energy at beta. So you see now I do have my scale like L for this particular average. So this satisfies the large division principle. And this F of lambda, in that case, is just a difference of free energy. And that's the general result. If you want to look what happens with the fluctuation of energy on the interval, 0 to L, is given by a difference of free energy, shifted temperature and non-shifted temperature.
Yeah, but the fact that the first step where you say, okay, they don't commute, but that's kind of then they do. I mean,
yeah.
Can it be that sometimes things can happen still like that?
Yeah.
I guess you checked, right? Like at least numerically that you get.
Yeah. So this is well checked in different ways, but so the way to think about it, they don't commute. You see what happens when things, some local thing, that can happen. Well, it can become very big if you evolve it in time, for instance, right? So even if it's a small thing, you evolve it in time. So e to the IHT, something small, can actually be supported on a big thing. But here, there's no time evolution. The time evolution in quote are these beta and lambda. So for finite beta and lambda, it should work. That's the general argument. You can actually make things more precise at small enough beta and small enough lambda. Like you can do Taylor series expansion and bound the terms. That can be done. I'm not sure how much has been done for that, but that can be done and then show that this is actually no problem. You can bound commutators now that. So you can actually, for small beta, small lambda, so large number, you can bound all the terms in there, and that would be correct. But yeah, so it's a bit of a non-trivial thing in the quantum situation. Okay. Yeah, another question? So this is the situation now. So this is a general thing, but now let me do something similar to that. Okay, similar kind of a non-commutator, blah blah. One can do more precise now, but similar to that. In the case of CFT to calculate this, now you see this is the general result for integration over space of a density, integration over time of a current. The general result is much more complicated. There is a general result, and I'll talk about it next time. But I cannot do a simple manipulation like that. Just don't work, right? Okay. But for CFT, I can do simple manipulations, and that will work because I have the expression left right mover. So let me do now this e to the lambda j of t in CFT. Okay. So now I want to do average e to the lambda j of t in conformal field theory. So make sure that I have all the steps right. So this is again. So this is so remember that j of t is what is the total current. So this is integration, say from 0 to t ds of the current, which is stress tensor t at minus s minus t bar at s. So one is right mover, the other is left mover. Okay, so it's relatively simple, right? Because of the left and right mover structure, I can rewrite everything evolve in time as things displaced in space. And that's why you can do all the calculation. Okay. And now this average is then, so trace, exponential, then I have minus beta h, so it's minus beta integration dx. Well, let me do the steady state that we had here. So there's integration dx from minus infinity to 0. No, sorry. There's integration dx. There's a beta left t of x plus beta right t bar of x. So in the steady state we had, remember that we were thermalizing the right mover with the beta left because they just see the left bath because the right mover, they come from the left. And the left movers with the beta right. That's how we thermalize the thing, okay? So that's our stationary state, okay? So I'm just calculating everything in the stationary state there, okay? So left and right movers thermalize in different ways. I could take any other state, but that's a good one to take, okay? And then I put also my exponential lambda integration from 0 to t ds t of minus s minus t bar of s. Now, you see clearly that I have integration over x of something, t and t bar, and integration over s, which is again the position here, the position, t minus s, t bar s. Okay? It's very similar to what I had there, where I had integration over positions and then in some region of space changing the beta, just in some region of space, right? Well, likewise here, in some region of space, I changed the beta left by this term, right, with lambda, and I changed the beta right because of that term differently. So beta left and beta right are changed differently. In fact, let me do sorry. Yeah?
I guess normalize too, so that.
Yeah, I have to indeed. I have to normalize everything. I put the 1 over z, and actually, I think this would work as well. But the calculation is much simpler if I do from minus t over 2 to t over 2 because it's all symmetric. It's kind of simpler. The whole thing would work as well, but it's a bit more tricky to see the detail. But it's the same thing, of course. Yeah. So minus t over 2 to t over 2. Anyway, it's a stationary state. I can integrate anytime, anywhere, everywhere in time. Okay. So I do that. Now, what I see is that on the region, maybe I do a little graph now. Okay. On the region, so I have space between minus t over 2 and t over 2. There's a change because of that. And that change is that beta left becomes beta left minus lambda for the t, and beta right becomes beta right plus lambda. So now there I have a different stationary state. So here I had rho beta left, beta right, okay? And there I have rho beta left minus lambda and beta right plus lambda. Different, as if the temperatures had shifted by this lambda. Okay? Different states. What I'm calculating is kind of free energies. And I should not forget the denominator where nothing is changed in the denominator. In the denominator is the same temperatures. So I put all that together and I find a simple thing, which is very similar to the difference of free energy that I had written there. In fact, exactly what I find, difference of free energies, right? So I find that this e to the lambda j of t goes like exponential t times a difference of free energy. So the region is of length t. And now I have free energy for beta left. So I have a free energy of the right movers, all right, F right, free energy for the t, okay, at beta left plus lambda, and I have plus, and it's a minus in front of everything, a free energy for the left movers, and it's that beta right, I'm probably inverted the two things, minus lambda here and plus lambda there. What is the free energy for the right movers and free energy for the left mover? Well, this is standard CFT things. F for right and left takes exactly the same form at some beta, and exactly pi c over 12, 1 over beta. So the free energy is just proportional to the temperature in conformal field theory, in such a way that if you do a dv beta of that, you get 1 over beta squared. There's a negative sign. You get 1 over beta square, and that's the t square form of the average energy. Right? The free energy generates the average energy. Okay? So this is a CFT calculation. Just pi c over 12, 1 over beta. You put that in here. What you find then is f of lambda is just, now put all the factors together correctly, C pi over 12 is beta left 1 over beta left minus lambda minus 1 over beta left plus 1 over beta right plus lambda minus 1 over beta right. So this is the formula for the scale cumulant generating function in a non-equilibrium stationary state in CFT, non-equilibrium stationary state for energy transport. So if I differentiate with respect to lambda, I get the cumulant of total energy transfer in a CFT for that thing. Right? It's a nice formula, so very simple, just a difference of free energies in the end, relatively simple. But of course, this derivation that I have given is very, very far from being rigorous. I mean, it's there are many terms now that. Now, this was the work with Denis Bernard, and we did try to make things a bit more rigorous now that, but there was always some little terms missing. In the end, it was a student who developed some diagrammatic approach for Virasoro, which kind of we could understand order by order. And eventually, later on, there's Kozlovsky and Christoph Gavetsky who gave a mathematical proof of this formula, like a big 50-page paper or something like that. And I think there was still some little step missing in the proof. So it's kind of relatively difficult to actually prove it properly, right? But the derivation, the physical derivation, is relatively straightforward. So yeah, so this is the SCGF in CFT. Now, yes, 2 minutes. Yeah, so kind of where I wanted to finish. I want to see kind of one last thing. In fact, this is very nice, and I can calculate average of total in the time integrated currents. And it's a good point to look at. Okay, now this satisfies a number of properties that I will come to. In particular, the fluctuation relations are satisfied. So I'll talk about fluctuation relations next time. It's a general relation for non-equilibrium steady state, and that this satisfies it was kind of one of the first checks of that general relation in interacting models, CFT, arbitrary CFT interacting models. Okay? But it's a general relation. And also, this can be generalized. So this whole technique, in fact, can be generalized to interacting systems, in fact, to arbitrary interacting systems, integrable or not, whatever, using hydrodynamic idea. So in fact, this whole thing is a hydrodynamic theory. Much like that here, that was thermodynamics. So here I could take any interacting system, right? And in principle, how it works. It's just thermodynamics. So similarly, this result is actually hydrodynamics. So you need to know currents and flux Jacobian, what is hydrodynamics. Okay. So I will try to explain a bit how this goes. So and yeah, but the one thing I want to finish with is the fact that physically, the quantity I'm considering, that thing, is actually not really good. Unfortunately, sorry about that. Because if you think about the quantum system, well, you don't measure the total current, time integral of the current. Well, you might measure that by doing indirect measurement, perhaps, right? You couple your system to something else, and then you measure the something else, but it always affects a bit the system, right? So you have to do very weak measurement, indirect, and maybe get a current. But then this is not the formulation, right? It's not trace exponential of an operator, right? So this is actually not the correct theoretical formulation for measuring total, transfer of energy in quantum systems. One thing that you could do, which would be the correct way of formulating, is what people call the two-time measurement. So maybe what I should do is measure at time 0 the difference of energy between left and right, and then at time t, the difference of energy between left and right. I can do that. But when I measure, if I do like strong measurement, I project with projection. That influences the system. And so the formulation here is that you would say, well, the probability for measuring E at time 0 and E at time t is trace, and then you have evolution of your projector at time t, and then you have a projector at time 0 for E0, and then you have your initial density matrix. So that's what you'd like to calculate, and then you would say, here, okay, and I erase that. And you would say, well, the scale cumulant generating function really, what is it? It's e to the T f of lambda will be just the sum of or the integration over this dE0 dEt of that probability distribution P of E0 ET exponential lambda of the total difference, the ET minus E0. And this is what I actually would like to calculate, right? So I have a distribution of things that I measure in the experiment, and energy before and energy after. Am I missing something? Yes, okay, that's fine. And the projection is I measure the difference of energy before and difference of energy after, and I get two different numbers, and I just calculate the difference of these two numbers. And that's the total thing that's been transferred over time, right? So the projection is for a particular operator, which is difference of energy between left and right points, or maybe just energy on the right as well, if you wish, something like that, right? So, and that would be the proper thing. You see, this is quite different from that. Okay, it's enable projectors and all that. But it turns out you can write projectors and all that in a certain way. You can message that, and actually you get the same result in CFT. But by the same type of approximation of non-commutating, neglecting commutators and all that. Okay, but you've got to massage things with it, so it's a bit more complicated the actual derivation, right? But in the end, you get the same result. For a similar reason, if you neglect all commutators, then it becomes classical again, and then you neglect all the quantum stuff. And of course, then you get back to that. But you have to argue a bit more. Okay, so this is even more complicated to actually prove than that. Okay, so and I don't think there's any proof for that. Yeah. Okay, so that's how I wanted to say today. So next time, fluctuation relations and how. So two things and how this follows from hydrodynamics and how this F is related to twist fields in general, and perhaps some kind of entanglement relation. Okay. Yeah.
Is there any question? The few during the talk, if you can have a few now.
So yeah, so there is not so much in high dimension, no. You see, in high dimension, what you can do as ever then is to use hydrodynamics. Okay, so we've done that in this paper, or you do higher DCFT. But we didn't have the full understanding, so I don't think we had the exact correct answer there. And now that we have some kind of theory, so supposedly we could apply the theory to higher dimension. Actually, yes, we did look at higher DCFT, in fact, for this F of lambda. But yeah, it's a bit complicated somehow to, there's no closed form formula, right? But yeah, so using hydro, you can get something. Actually, I don't remember the precise state of affair. I think my student had obtained some numerical result for F of lambda using hydro in some way. Yes. But comparison with actual quantum system is very difficult. Right? I don't think this formula has been checked against quantum system at criticality. I mean, the current, yes. I'm not even sure if the second cumulant has been, maybe the second cumulant, but not the full formula. Okay. Yeah. So and then in higher D, it's more difficult. But yeah, I guess the thing is the hydro formulation, which I'll discuss a bit next time, that will be applicable in higher D in principle.
So when you do the hydro, you really mean hydro finite
yeah, so this is earlier hydrodynamics. So forget about diffusion. This was your question about the next correction term. The correction, the ones with the scope of T will be an effect of diffusion, supposedly, although this has not been computed. But the earlier hydrodynamics, so the ballistic bit of it, where you have you missed the class, but I'll show you the thing. I mean, I'll remind Friday if you're there. But yeah, so the basic hydrodynamics, if you have a momentum, energy, so you have a current and a few conserved quantities, you take these conserved quantities, do their earlier hydrodynamics and use earlier equation, essentially to get something about that. Yes, earlier equation.
Depends the hydro about which state you do it, because if you look at critical state, the hydrodynamics above the ground state.
Yes.
Then you find that fluctuation above the hydro actually is stronger.
Yes.
So you have a long-term tail.
That's right. Yeah. Mm-hmm. So okay. So hydro at 0 temperature, you have long range correlations and all that. Okay, that is all well defined and nice. Yeah. That is all nice. Yes, indeed. And indeed, so and what you want to do, but so these driven state, they are still kind of look like Gibbs state or something, right? They have a Gibbs form, and they have, I mean, it doesn't matter Gibbs form, but at least they have still decaying correlations. They still have decaying correlations.
Yeah, but the first point is the decay of the power.
Yes. And that's fine. And that is fine. Yeah, that is fine if the decay has a power that's large enough. Usually it's like 1 over x squared, and that is fine. So that Euler hydro is not broken by that. It's okay. Everything works. So that's okay. But if you do so, yeah. So I think that there are different questions there. So, sorry? Yeah, that's right. Correct. But yes. But at the Euler scale, you talk more about the diffusive scale when you have quantity, and there you have problems. Yes. But at the Euler scale is very, very, very large scale. So it's very stable under correlations. You need to have very strong correlation to break it, and you don't. And the 1 over x squared or most power laws don't break it actually, and even it's a bit more complicated. Okay, so there are different things. So first of all, okay, what is the state? Does it have strong correlation? So it may or may not have. Okay, if you have a driven diffusive system, it is known to have 1 over x type of correlations, driven diffusive. Okay? But here I'm looking at ballistic system for a large time. Okay, and these will look like boosted thermal state or things like that in typical non-integrable systems. And these have nicely decaying correlation, even exponential, then everything's fine. Okay? In CFT, fine temperature CFT, these states now that they are exponentially decaying as well, because I'm just looking at Virasoro sector, this H and P and all this, it's fine. Okay? If I were to do that at 0 temperature, then okay, everything changes for the fluctuations, and then it would not work. Yeah, but it's fine. You see, this has exponentially decaying correlation, right? This stationary state, because it's just exponential of H and P, and that's okay. That's exponentially decaying. When one has to look case by case, right? Certainly. Yes.
Otherwise, you get divergences. Can we either as a difficulty or in the redirection of the free level?
Yes. Yeah, perhaps, but so even in higher DCFT, you look at the stationary state. So infinite time, you take infinite time from this, T left, T right. Okay. At infinite time, the stationary state is boosted thermal. That's it. No, it doesn't change. I think what you're thinking really is like the approach to it. Yeah. That is clear. That is clear. And you boost that, and it's okay. You don't lose the exponential decay. But what you're thinking is maybe the approach in time that is non-trivial. Yes, but well, the large time limit is well defined for all local observables. So and that's a state, and that's this boosted thermal state. So that's okay. And this have all nice hydrodynamics. Yeah, it does. I mean, the boosted thermal state has decaying correlation, exponential decaying correlations. No. So take the thermostate, boosted thermostate, exponentially decaying correlations, and you can do Euler hydro of that on top of that without current correlation at long time. Okay, well, okay. So what you can just, I don't know, maybe I should stop. Okay. Stop the recording. No, so what you're talking about? So if you have correlation between two operators, say 0, 0, and then O prime xt. Okay. Correlation in time, space time. So correlation in space, they will decay exponentially, right? In thermal states, take a thermal state, even not, whatever. Okay. Correlation in space time, they don't necessarily decay exponentially. I agree. Yes, that's for sure. Okay. Where do they not decay exponentially? Well, for instance, if I put these at equal position, they might not decay exponentially if I have a hydro mode that has velocity 0, which is typically the case. The energy mode has velocity 0 in equilibrium, right? And it's something that kind of, yes. Well, yes, precisely. Gap is diffusive mode. Yeah. Yes, exactly. So that's some kind of diffusive mode, supposedly, and all that. In 1D, actually, you have super diffusion, so it decays even. Yeah, exactly. So there you have power, like maybe like 1/√t or something like that, right? And now the total time integral correction, yeah, blows up, and the cumulants don't have that scaling. Correct. Yes, but if you do, yeah. So that's correct. So this whole theory, so the large-deviation principle will fail if you try to do it along a ray that is at a hydrodynamic velocity, and then the whole thing fails. Correct. Yes. But if you are in a non-equilibrium steady state in typical non-integrable systems, okay, where you put some momentum. So I should put it there. So there's some momentum there. Okay. So you put exponential minus beta h minus vp with some non-zero v. That changes the velocities. Okay. The sound velocities are somewhere else, are not symmetric, and the heat peak also now has this velocity v, actually, right? So now it's no longer true that you have 1/√t at equal space position. The heat peak is going to go at some velocity, right? And now this is now well defined, and you can do the large deviation, and it's going to be the ballistic scaling of the large deviation principle. So the positions where, so as you change the state, the velocity may come to 0. And now this is a dynamical phase transition where your free energy blows up, your kind of dynamical free energy blows up, and the scale cumulants don't exist anymore, and then the large deviation principle is broken. So yeah, so it depends indeed on this velocity. Yeah, that's yes.
Space-time local operator.
Yes.
In turn, then k goes to 0 first, and then omega goes to 0.
Yes. Yeah, but yeah, k goes to 0. You take the totals current in space. It's not quite what I'm doing here, actually. Yeah. No. Yeah. Yeah. Yes, and the viscosity. So this is the Kubo formula where you integrate. You have the total current, and you subtract the Drude weight, and you integrate over time from 0 to infinity. It's something like that. But you've got to subtract the Drude weight, because that's the ballistic bit. Subtract that, they integrate from 0 to infinity, and that might be finite or not. Yes, indeed. And that's the diffusion or cyclometric diffusion coefficient. And if it's not finite, yeah, then you have a blowing up transport coefficient. But this is actually not relevant to what I'm doing here, because what I'm doing here is all at the level of the Euler scale. That's the diffusive scale. So in a sense, at the level of the Euler scale, I will see if I have a large deviation principle or not. If I don't have one, if it fails and all that, then it may be because of that mode that's there, and then the correct scaling will come from the diffusion of that mode, and I'll have to do a bit more work, right, and really take into account this higher scale. But if it's correct, if there is a large deviation principle, ballistic type, then there's nothing else to do. You don't need to go to the further scales, and then you have the right answer. And typically in this boosted thermal state at equal position, it's going to be fine, because you won't have a mode there. Yeah. Yes.
So if that's fine with you, we can discuss this over lunch.
Yes, sorry.
Thanks a lot.
Thanks.
Thanks, Valama, again.
Thank you.